So I thought I'd make a quick video of that PowerPoint that I managed to get through some of the questions for in my first class, and the other two classes we just had too many questions that we went over in class, too much discussion to get to it. So the first question was the tree diagram question. I wanted to give us one more example to do a warm and fuzzy question together. So I have this ridiculous example that I came up with one semester while I was in Idlewild about to go on this wine and art walk, and I had to write an exam. So I was not excited, but you can see exactly where my mind went. I said, Kelly is spending the weekend in Idlewild for a wine and art walk. She estimates that the probability she will drink too much wine to be 30%. So I clearly thought I would be a responsible human and made my probability of drinking too much 30%. Let D be that event. So the only thing that we're talking about is drinking too much wine here, right? Nothing else. So if we wanted to translate that to begin with, we just found the probability of D by itself, nothing else, is 30%. This is already letting us know the starting point for our tree. The thing by itself is our two potential timelines that could happen, right? If I wanted to start thinking about a tree here, I have space on the next page. There are two things that could happen in this timelines, right? One, I could drink too much. There's a 30% chance of that happening. The other timeline is those pores are not very generous and that I do not drink too much. So these are our two possible timelines. And then we'll go ahead and see what else could happen once we're in one of these two scenarios. So if we keep reading, we know the next thing to come has to be a conditional, because that's what a tree is all about. And we have our keyword if she has too much wine to drink. So this is in the drunk situation. She estimates the probability that she purchases art on the walk to be 85%. And you can see later on, we've decided to let P represent that she purchases art. So if drunk, probability of purchasing art is 85%. And that's already giving us the way to split up our tree again. Oh no, giant red green pen. We're now talking about this particular timeline, right? She could be drunk. In either way, she's drunk. We know we're in this timeline. Two options. You can either get art, yay, or no art. I was very excited about buying something to commemorate this outing with all my friends. And we could even at this point continue on and figure out the probability of being drunk and purchasing art and not purchasing art and being drunk, figure out what those values are. Now, if we read our last sentence, we see if she does not have too much wine to drink, which is what we knew. We needed to split up the not drunk possibilities, right? We knew that that's what needed to happen next. What could happen if she doesn't drink too much? We still know the two outcomes are going to be the same, purchase or not purchase. But now we see the probability that she purchases art will be 65. So they gave us the same probability up here, 65%, just for the sober potential. And that means there's a 35% chance of not purchasing art. So, like I said, I really wanted to get some interesting pieces of art at this, complement this wine and art walk. And to find all these probabilities, we're just going to multiply down our rows to find them. So I guess I could have used my little calculator on my my screen, but I'm not going to. 0.255, 0.045, it's terrible. 0.455 and 0.245. And now remember, if we want to, especially if this is a test question, it might be worth taking a little bit of time making up a table with purchase, didn't purchase, drunk, not drunk, and inputting all four of these values into my table so that way I can answer any question really easily from the contingency table. And it sort of double checks everything. We can see probability of drunk is 3, not drunk is 0.7. We've got our probability of not buying art and our probability of buying art, which I hope are right because I refuse to get out a calculator for those. So then we see the 3 questions I said would come next, or I said there are 2 guaranteed questions, and here are the questions that came next on this particular exam question. The first is one of the ones I said. What is the probability that Kelly purchases art on the walk? Nothing here about being drunk or not. So this is the probability of just P, which if we made the table is super easy. If we didn't make the table, then we're sitting there and going, okay, these 2 things both represent P. Let's add them together. But with the table, we can just pull off P by itself. Or 0.71, I guess the 0 is unnecessary. Next one says probability will purchase art, so we have our P, but won't have too much to drink, so not drunk. Looking for a keyword here. There's no and, there's no or, there's no if, of, or given. We do have a keyword we have seen before in but. And but, remember, is probability of P and D complement. But is just another way to say and, another conjunction. There is no calculation to do here. This is something we can pull directly off of our table, P and D complement, or right off of the last little ends of our branches of the tree. So it looks like this is 0.455. Our last probability here, if does not purchase art, so P complement, and we know we have that if, so this is a conditional statement, was a probability she does not have too much to drink. All right, so again, D complement. And this is found using the and over the thing we know. If you don't trust me on that, look at our formula sheet. Whenever we need a conditional, whatever was here, we turn it into an and then we divide by the thing we know. So that's all I'm doing to get this formula. And then these we can grab straight off the table. This was 0.245, and this was, well, the opposite of the other one, 0.29. Which according to my calculator is equal to 0.8448. So anyways, the 2 questions I said are guaranteed to be on the test, right, are the opposite marginal and the opposite conditional. This is just a bonus. But the other 2 guaranteed to be there. And like I said, as you go through all the sample exams, look and see this again and again and again. All right, the next question I put in here, not even a question, I just wanted to show you what it would look like to have a table where our 2 events were independent and how that would look if we were to test them. Because almost every example we've seen, the events have not been independent. So if we wanted to test independence in this and see if this particular setup was independent, we could use our independent rule. Our and is 0.24 is equal to A by itself and B by itself, right? I'm just grabbing these off the table, and A by itself and B by itself. And if we check that, sure enough, if I do 0.3 times 0.8, they equal each other. Yes, they're independent. We could also check this using the probability of A given B. If you remember this formula, right, we just used it on the last page. This is how we calculate it. If we're indeed dealing with something independent, what should happen is we could change this to probability of A times B. The B's we cancel. This is just the probability of A. Knowing B didn't give us any new information. So the probability of A is the probability of A regardless of what the heck's going on with B. So we could try this out. A and B is 0.24. Divided by B by itself is 0.3. We get out 0.8, which is the probability of A. And we can really prove this to ourselves by looking at the opposite version. Because here, now we're doing the probability of A and B complement all over the probability of B complement. This is 0.56 divided by 0.7, still 0.8. Basically, if you're in B or not in B, there's an 80% chance you're in A. It does not change. These ratios here, between this, or whether we're looking down the rows or across the columns, the ratios are consistent. That's what makes these 2 events independent. Now, why we don't see many of these independent events in class is because by the true definition of independence, these have to be exactly 80. We will eventually look at a statistical definition of independence where like 0.76 and 0.8 might be close to each other. But for now, this is our mathematical definition of independent. And if they're not equal, they're not equal. So it's very hard for things to actually be independent when we're talking about these types of events. Disjoint, this is what it looks like in our table to show an example of something that would be disjoint. Here you can see the A and B, that probability is 0. If you were to draw up a Venn diagram for this, the two circles would be separate. There is no reason to have any overlap because there is 0 probability of overlap. So I just wanted to sort of show you, here's what the two things look like. I know there's no actual question with it, but I think there's a lot of students kind of going like, well, when does it independent? What does that mean? And so what it means is that the ratios are the same. You could see this maybe with like students, if you had male and female, and this was, you know, as I said in class or in my lecture, pizza, no pizza, like in theory, the ratios should be consistent across the two different groups. Even if there are more males than there are females, you should still have the same ratios because there shouldn't be a relationship between your gender and whether or not you like pizza. All right, so we've got some examples here for testing independence that you could go through on your own. This one, they've given you an and. I've given you an example here of whether or not figuring out that something is independent or disjoint based on just common sense or sort of critical thinking. And another one of those same types of questions. So that sort of concludes all of the basic ones. And then we get into this, let's see all the different questions that might occur. So this is where I really wanted to start this video because I think the other ones are kind of basic. So this particular question, first thing I do when I glance at it is I see there are a bunch of different percents running around, which means that we're definitely in a part 4 question where we're dealing with probabilities. We're not in the, you know, normal questions or the binomial questions because they don't have all this stuff going on. So we read through once. You'll believe there's a 20% chance you'll earn an A in your RWS class, which by the way is a class at SDSU. This is an old question. 10% chance you'll earn an A in your econ class. You also believe there's a 26% chance you'll get either an A in either class. If these values are true, what is the probability you'll get an A in both classes? Okay. So let's go ahead and use R to denote getting an A in RWS. And let's make E getting an A in econ. So what we have now is the probability of R, an A in RWS, is 20%. The probability of E, an A in econ, is 0.1, so a little less likely. Now we need to figure out this percent, what is it, and what is the thing we're looking for, what probability we're looking for. So if we read through the 26% chance you'll get an A in either class. Either is our or, right? So we know this. And then we also have, we're looking for the probability of an A in both classes. And both is a way to say and. So now it's up to you to go, okay, well, how do I find an and? And this is that question. This is a formula question. That's what this falls into. If you were trying to figure out what the different types of questions are. This would be a formula question because you can't use the table or the Venn diagram to immediately get your answer here because they're set up to deal with ands. And we're looking for the and we have the or. So this is where the or formula could definitely help you out because we have this as our or formula. Right, the union of two events is equal to the two events added together minus their intersection. So in this case, 0.26 is equal to 0.2 plus 0.1 minus something. 0.26 is equal to 0.3 minus something. Our something is 0.04. That's our probability of getting an A in both classes, 4%. So that's it. But this is a formula question because if you didn't do all of this work, it would be very hard to continue on. All right. Next one. We see this at the bottom. Use the normal approximation to the binomial. They're putting it out there that we're dealing with a binomial, which means you must have an N and a P. And then they told us to do the normal approximation. So if we look, we see 79% rely on their own vehicle. There's my P. We're selecting 250 workers. There's my N. And we want to find the probability that more than 180 rely on their own vehicle. Now, to do the normal approximation to the binomial, we know we need to draw a normal curve. But for a normal curve, we need to know what the heck our mean is. So that's where step 1 comes in for this. We can find the mean of a binomial, just n times p. We can find the standard deviation of a binomial. It's the square root of npq. I'm running out of space. I will make it work. So our mean ends up being, I guess I'll use my cute little on-screen guy. You know I can move you about, calculator. Sorry, I'm moving this very slowly. All right, so we're going to do 250 times 0.79. So our mean is 197.5, and our standard deviation is the square root, square root 250 times 0.79. Yes, I could have just done answer, or that number right there, times 0.21. Our Q is just 1 minus our P, 6.4401. So our mean is 197.5. And we are interested in more than 180. So 180 is somewhere below 197. More than would tell us we're shading to the right. And we can find this by doing normal CDF. 180 is our lowest point that we're interested in. We never stop being interested, so we'll just throw a absolute crap ton of 9s in there. And then our mean that we found, and our standard deviation that we found. Then we should be good. So distribution, 180, crap ton of 9s, 197.5, and 401. Looks like our probability is 0.9967. All right, so this one was really easy to tell what it was, what type of question, because it had to tell me. There was no other way to let me know to use the normal approximation besides pointing it out. All right, this question is making it really obvious what type it is. Immediately jumps off the page, I see normal. Now we have 3 different types of normal questions. We have our direct, our inverse, and our tricky inverses. We see right here, we have a percentage, so this is either an inverse or a tricky inverse. And if we read through, we see that we have our standard deviation. We know our cutoff, and we're looking for the mean. This is a tricky inverse question. Our first step, is to draw our curve. We don't know the mean, that's what we're looking for. But we know 4% are above 340. So above gives me a keyword telling me shade to the right. And that's 4%. And then this is 340. So our value, whatever it is, has to be less than 340. So if we do this, we can go, okay, step 1, find our z-score. The z-score is from a similar distribution, but centered at 0 with a standard deviation of 1. But we're going to find the corresponding z-score for that. To do that, we're going to use inverse norm. And we need to give it a left side probability of 4% on the right side, 96% on the left. So I'm going to feed inverse norm 0.96. And remember, if you have a calculator that requires that you put in the mean and standard deviation, the mean for a z-score is 0 and the standard deviation is 1. It does not matter that you have a standard deviation up there. You want a z-score, and z-scores have a mean of 0 and a standard deviation of 1. So we pop out a z-score, hopefully. I guess I'll do it on my little calculator. 0.96. And we get a z-score of 1.7507. And then step 2, This is when we go to the formula sheet, grab that formula off of it. We know we were dealing with a normal question, so immediately we're down here. We're not going to get distracted by this mean or standard deviation formula because we don't have a binomial. We're doing a normal question. And this formula, since we did an inverse, is going to help us out. X is equal to z times sigma plus mu. X is equal to z times sigma plus mu. Our x is our cutoff, so 340. Our z is the thing we just found, 1.7507. Our standard deviation, now we get to use that 35. And the mean is what we're looking for. So first thing I'm going to do is multiply these together. Try I'm not busting out the online calculator, the on-computer calculator. 340 is equal to 61.2745 plus our mean. And if I want to get it by itself, I need to subtract this from both sides. So we end up finding that our mean is equal to 278.7255. Technically, I should put some units on here, but we don't have any. We're just talking about test scores, so that is perfectly adequate. Whew, more of this, huh? We keep doing more of these things. All right, next question. Before I even read anything, I see a percent and a number, which is leading me to think this is probably a binomial question, but I'll read to actually make sure. Suppose it is known that 30% of adults have hypertension. We randomly select 14. What is the probability that more than 3 of them have hypertension? So indeed, we have a probability of people having hypertension, a probability of success. We have a number of people that we are selecting, and then we are looking for a probability that more than 3 of them, 3 is our counted up number, our number of successes, have hypertension. So you can make your cute little number line if you want. I know a number of you hate me for this, but I'm going to keep doing it. We're interested in more than 3, so that's all of these values. So if we're going to realize, okay, right away, N and P means we're dealing with a binomial question. I've circled the right side, which means I need to do a 1 minus, and then I'm going to use binom CDF of 14.3, and we went up to 3 here. So whatever the heck that is. So this was our binom question, and it was a CDF question. So like I said, as you go through, you're going to see, well, what type of question? As you do all the sample exams, or even if you don't have time to do the last 2 sample exams, go through the blank versions and just identify the question types. That will do you so much good. I'm not even going to figure out what that probability is. Don't care. Here we have another, this is actually a formula question. You won't know that ahead of time, but we see 2 different percents, which means this is probably a probability question. We see Roger Federer made 64% of his first serves. So probability, I will just put first serve for here. F stands for making the first serve in. Not a fault, crazily enough. I'm being lazy. 64. Given that he made a fault on his first serve, so this is the opposite. Maybe I should change my fault. Maybe I should make this made for the first serve. So this is, a fault is made complement, right? He made a fault on his second serve, so also an MC, but this is on the second one. Oh, this is getting confusing. But then we're asked, what's the probability he makes a double fault? So faults on both the first and second serve. So, oh, this question, I'm sad. It's not even easy to do with the probabilities because we have this, like, maybe this shouldn't be M, this should be, maybe this should be, I keep trying to come up with new numbers or letters. Let's just call this A. A is making the first serve, so this would be A complement. And let's call A is making the first. And let's call B making the second. Whew, this will work. My God, it took me long enough. So this would be B complement. So the other probability we got here was given A complement, if he makes a fault on his first serve, that he also makes a fault on the second. This is a 6% chance. And we want to know about the probability of A complement and B complement, faults on both. Well, we could use the formulas. The and formula is told to us that it is a given multiplied by the thing we knew. But this question in particular, to me, is easier to set up as a tree and sort of see the tree diagram of it, especially because we have like one event that precedes the other one. So when Roger Federer gets up to serve, there are two things that can happen on the first serve. He can make it or he can fault, right? And we know there's a 64% chance he makes the serve and a 36% chance he faults. Now, we don't know what happens if he makes it. Well, if he makes it, there's no second serve, so this branch of the tree just dies. But if he faults, there are still two options, right? He can make it or fault it. And we know if he makes a fault on the first serve, he makes a fault again only 6% of the time, which means that this happens 94% of the time. And if I wanted to find F and F, two faults, well, I could just multiply down this row. 36.36 times 0.06. So to me, the display is way more useful here. I had so much trouble trying to come up with things to use in the notation. But since we had one thing happening and then another, it was actually easier to sort of visually see what was happening in a tree. Again, this to me was an extra credit question I put on one test. It is far beyond what I normally do in a class. All right, 3 more separate me from going home. So I'm not going to do a great job on these. I'm going to just get them done. So here, I scan. The first thing I see is normal. I know we're dealing with a normal question. I already did my tricky inverse, so I'm thinking this is either a regular inverse or a direct question. And then we see, oh, we're looking for a probability of less than 120. So this is the direct question. So if we were to draw our curve, we know our mean, oh, they must have told that to us, is 107.62. And we are interested in it being less than 120. So this would be a normal CDF question. I'm not even going to finish this, because my point to you guys is, as you go through the test, yes, once you figure out how a direct question works, it's more about identifying a direct question. So knowing right away that I'm going to use normal CDF, I'll have no problem doing that on the test, because I've done enough practice on that. It's just a matter of recognizing that that's what I'm supposed to do. So the next question. In a group of 20 people, there are 4 with red hair, 9. Oh my goodness. You can already tell what's happening, right? 2 people are selected at random without replacement. So we know this is one of those questions. We're going to draw our little diagram and think about what's happening. We're asked for the probability that exactly 1 will have red hair. So we need 1 redhead and 1 not redhead. And the exactly 1, remember, is the time that we need to multiply by 2, because I could have gotten the redhead first or second. And then we think, all right, if we had, I'm drawing people, by the way, 4 redheads, we have our 9 blondes. This is my real, I just like drawing, so you guys get stuck with this. If you've actually made it through 28 minutes of video, you get to watch me draw. And then, oh, I don't have brown. I'll just make them blue hair. That'll work. And then I have 7 with blue. 1, 2, 3, 4, 5, 6, 7. 7 with brown hair, which is represented with blue. So, 20 total people. Probability of the first person being red, well, that's just 4 of the total 20. Now, once we select this person, we have to take them out. They are no longer being considered. They've already been selected. So now we think, okay, well, what's the probability that somebody does not have red hair? Well, that's everybody over here. These 9 people plus these 7, so there's 16 people that don't have red hair out of the total 19 people left. So that's our calculation that we're going to do to figure out the probability of exactly 1 person having red hair. All right, final question. Thank goodness. As we read through, scanning, normally distributed. It's our normal question again. We have a mean and a standard deviation, so thankfully it's not the tricky one. And then we're asked to find the 3rd quartile. So we want to draw our picture. All right. Our mean is at 80.5. 3rd quartile, what does that mean? Well, 3rd quartile is the 75th percentile. And that means it's above the mean, right? It goes Q1 median, Q3 max. So we have 75% of the values below whatever the heck our third quartile is, which we don't know. And this is what we're going to use inverse norm to find. Nice thing about a percentile, or in this case a quartile, is it already gives us area to the left. So we're just going to pop that in with our mean and our standard deviation, and we've got our answer. Boom. And since I wasn't given any units for this blood pressure, I can leave it unitless. But normally we should put our units back on.